So the problem with this is to find out what is the linear acceleration at the center of gravity upon the application of this 100 Newton force. That's what we're trying to figure out. Okay. So I know we won't be able to finish the problem, but let's start solving the problem. First of all, exactly the same approach, right? You know that we have the force equilibrium, summation of the force. Now you can also use the tangential component or the angular component. So that means the same formulation. For the normal component equals to mass times Ag, normal component, and the tangential component Ft equals to mass times Ag at the normal component. And that's of course the moment equilibrium, summation of the moments. Now here you have to be careful. Which point should we choose? Where should you choose to take the moment equilibrium? Where do you think we should choose? Should we choose B to take moment equilibrium? Or should we choose G, center of gravity, for taking moment equilibrium? Or should we choose A? Where should we choose? It is customary to choose a stationary point for taking moment equilibrium. Why? Because in some cases, like in the case of instantaneous center of velocity or zero velocity, in some cases, you may choose a non-stationary point for taking moment equilibrium. But overall, if you choose a stationary point for taking moment equilibrium, that means you're going to account for most of the dynamic terms. Therefore, in this case, we're going to take the moment equilibrium at point A. Because by taking the moment equilibrium at point A, you will account for the tangential, normal component for the linear acceleration at point G. You also account for the reaction force at point B coming from the spring. This way, you will account for all different kind of forces. Of course, what you're going to miss here is just the reaction force at point A, right? And because this is the hinge, so that means at this point, point A, there's no moment here, which will make this equation much easier because the left-hand side, you know it's going to be 0. There's no moment at point A. That's the boundary condition. So the formulation-wise here is just going to be the same. It has to be m times Ag, of course, m times depending on the positive or negative, depending on the direction of rotation. Ag tangential, xy bar plus Ig times alpha. All right. So any questions about the formulation? Now, of course, the general form of this is these two could be positive or negative, depending on the directions that we consider. And we have not defined the positive direction of this moment, which is why we don't know whether the product of the normal component is going to produce a positive moment or a negative moment. That's why I will lead them to be positive, negative, positive, because we don't know. We haven't defined this one yet. So it could be positive, it could be negative. Okay, and of course, the same thing with with the angular acceleration. We don't know if it's positive or negative because we have not defined this to be positive or negative. But in this case, you know that the application of this 100 Newton force is going to push the simply supporting beam downward, right? Therefore, the angular acceleration will certainly be going in the clockwise direction. So to make everything easy, you may want to assume positive direction to be clockwise because you know that's the direction of motion. So by choosing this, you will make everything relatively simple. Any other questions? All right.